We're sort of pressed for time, but if people are really keen, I can dig those out. Just let me know with an email or get some consensus. I know there's a big group of you all in the same program. If you all want it, I'll do it. The other thing we didn't like is to work out the paths, we had to do these integrals with highly oscillatory coefficients, and that wasn't very good either. But here's the interesting thing, right? Let's suppose that I wanted to work out the values of f on a grid. It's the same thing we're going to do in reverse. So this is f at jh, right? And the h is 1 over a. Right? Okay, so then I'm going to get the sum n equals minus infinity to infinity f at alphas, and then I'm going to have e to the 2 pi I alpha jh. Okay, let's just think about that for a minute. So let me refer to my notes so I can try and get this right. So let's just think about this for a minute. Okay. Oh, there's some tricky way to look at this just right, which I'm missing. So let me try and work my way up. I can't tell, so can't distinguish modes that are an alpha from alpha plus or minus n, alpha plus or minus 2n, and so on the grid. Right? If I change alpha by n, right, and h is 1 over n, then I'm just changing this argument by a multiple of 2 pi, right? And so when I'm looking at the value on the grid, I can't tell whether I'm getting f hat alpha or f hat alpha plus or minus n, plus or minus 2n, and so on. So now if you looked at these values on the grid, this, by the way, this is called aliasing. Which maybe you've heard of before. If you've done any electrical engineering stuff, okay, some nods from electrical engineers.
Engineering physics. Engineering physics.
Engineering physics, okay, yeah. So this is just a phenomenon where high frequency information is seen as low frequency information on grid. And you know, this is a real issue in all kinds of different situations, right? You know, you're doing analog to digital conversion at a fixed rate, and you're gonna, if the rate's not fast enough, you're gonna get corruption of the signal because there's high frequency stuff that shows up in the wrong frequency. Okay, so I'm missing exactly how this goes, and maybe oh, okay, yeah, maybe I can do this. So I can rearrange this sum to go from have n terms, because there's only n terms, right? All the other stuff is mapped on to the n terms. And I'll have, well, maybe I can even do 0 to n. So it's going to look like a transform. Right, and then what comes in here is everything. So I'm going to get alpha, or I think I use L in the notes. Minus infinity to infinity. I'm going to get f hat alpha plus n times L. But I haven't changed anything, right? Because of this property. Right, but this now looks like a discrete Fourier thing, right? So that means if I take my values of f on the grid and I do the fast Fourier transform, so this is also fast, I'm going to get some things that are so maybe I should make these little f's. I'm going to get some f alphas, and they are exactly these things here. Okay. And let's just have a look and see what we're expecting the f at alphas to look like. Well, okay, so they're on a discrete set of points. But remember, when f had a lot of derivatives, these had strong decay in alpha, right? So it was like 1 over, alpha to the power of the number of derivatives that you have. So if f is really smooth, then you're expecting, pretty fast decay. Right? And so if you pick n big enough so you're capturing most of that stuff, right? Then if you're sitting here and you're going, well, this I want this mode, right? This is important. But what I get is not just that one, right? I get this one, but then I've got to have, n and 2n and minus n and so on. They all get added in. But if you pick n big enough and f is smooth enough, that error is really negligible, right? Right, so this is in fact a good approximation. Okay, now you have to be a little bit careful. Now I've actually relabeled these so that they look like fast Fourier transform modes, right? But that's labeling them from 0 up to n, right? Which is, not really what I want, right? I want to label them from minus n over 2 to n over 2. So this will be a good approximation for f hat alpha if I look at alpha going from 0 to n over 2. And then it'll be f hat, now I'm going to have alpha going from n over 2 plus 1 up to n. Right, but as I go out here, right, I really want them to be those guys. Okay, so let's see if I can get this right. It should be alpha minus n. So, remember I told you, right, when you're doing this fast Fourier transform, you've got wave numbers going from 0 to n, but that's not what you want, right? You want a symmetric window of them keeping the important ones. And when you're dividing by alpha, it should be the alpha going from minus n over 2 to n over 2. So when you're implementing this, it's on the next assignment. Okay, call the fast Fourier transform, that's easy. Call the inverse transform, that's easy, but this numbering is something you have to probably play with a little bit. Okay, so now you can see the algorithm, right? I evaluate f on a grid, right? I take the transform. I get n numbers, right, which are labeled from 0 to n. But now I want to relabel them so that they go from minus n over 2 to n over 2. And with that labeling, I'm going to divide by that. I get these things. And then from these things, I can evaluate values of u on the grid using the inverse transform, inverse of the discrete Fourier transform, which is also fast. Okay. Just a little bit of a warning, right? This is simple in this periodic case. If you have a bounded case, so let's just suppose we've got the case with Dirichlet, homogeneous Dirichlet boundary conditions. Now the eigenfunctions of that problem, the series solution would be the Fourier sine series. The Fourier sine series does not have spectral convergence. Right? So remember, when it says spectral method, it's not about using the things, it's the convergence rate that you're talking about. And so in this case, you have to use Chebyshev polynomials, where you can also use a fast Fourier transform to evaluate them. But the points where you evaluate it get bunched up at the boundaries. And that's, okay, we're going to care about Chebyshev polynomials when we talk about the conjugate gradient method. They are the optimal, the zeros of the Chebyshev polynomials are the optimal interpolants. So your question number 3 on the last assignment, that was the quartic Chebyshev polynomial that had that property that the maximum and minimum are all the same. And when I write out how you generate these things, you'll see why they have that property. So it's just one of those things where we'll look at those polynomials, but let's not implement that. But now you know that's what you would have to do if you wanted to do a spectral method with a problem with boundary conditions. Okay, because you needed really high accuracy for something you were doing, some scientific problem where you need 8 digits of accuracy on something. I'm blanking on what that would be, but there are problems like that out there. Okay, any questions on this before we go on? Okay. Well, we got another formulation of this problem, and another method that comes with it. It'll be the finite element method. So let's make a start. Sure.
So you might be covering this later, but I was wondering how the Fourier coefficients still need to be integrated. So when we're comparing, I guess, spectral methods with the finite difference method, don't we still need to incorporate the fact that even if we have to use a quadrature method, and that won't give us.
No, because at the end of the day, remember, you get values of u on the grid. So you just compare those to the exact solution in maximum.
I see what we get those values of u, and then we fast Fourier transform that.
No, no. Okay, maybe I'm misunderstanding your question. So you're testing your spectral code, right? And you've got this exact solution. Right, or you can do it in the interval 0 to 2 pi and have e to the cosine. So that's the example, right? And then the f you get just by plugging it into the equation, and whatever comes out is the f. Right? It's written in the notes, I think, so you don't have to do that yourself. So then you have the f, you evaluate it on the grid, you take the transform.
Okay, yeah, I see.
And then those coefficients you divide by the right alpha with 1 over 4 pi squared alpha squared plus 1. Right? And then you get the u hats, and then you inverse transform to get values of u on the grid, and then you just compare it to the exact solution. Right? And what you should see is you've got some pretty big errors when n is here, and then they start to get smaller, and then suddenly you'll increase n by like a couple, and then a couple more, and you'll be at machine precision. Right? So that's why these have a different sort of feeling, convergence feeling than finite difference methods. If you double them, you'll just have something, and then machine precision, right? But so it'd be nice if you kind of look at some of the ends in between to see the tail really going down. Have I answered your question?
Yeah.
Yes. Okay. Yeah. This is just a code debugging thing, right? This is you're just testing it on a solution just to make sure your code's working. And if it's not working, almost surely it's the changing to the right alphas that is the problem. So that's in my experience. Okay, so let's talk about the weak formulation. So we've already seen ways to get weak solutions, 2 different ways. One is if you've got the Green's function, the f that you put in doesn't have to be even continuous. And then we have the Fourier series solution, right? We can define the Fourier series coefficients even if f is discontinuous. And L2 is the right space to look at in that case. Okay, so I'm going to do a formulation here where it's designed to capture weak solutions like right away. Right? This is the whole purpose of it. So I'm going to take this, and I'm going to multiply by a CP1 function. And these things always get called test functions. Testing the equation with the function. So I'm going to have minus u double prime c plus u times c is equal to f times c. And then I'm going to integrate from 0 to 1. And I'll integrate by parts. Right, integrating my parts, I take a derivative and I move it over there. And there's no boundary terms because u is periodic and phi is periodic too. Right. The CP1, this is continuous functions that are periodic, and also the first derivatives are also continuous and periodic. Okay. And then I've got the u times phi. Okay, and this is, if I've got this problem and u is the solution, then this is true for every function b that I try. And remember, I said as long as you can take limits in the H1 norm, then if it's true for these functions, it will be true in the limit. It'll be true for all b in this bigger space, HP1. So that's where you've got square integrable derivatives and function values. Okay. You can see right away why this is called the weak formulation. For you to satisfy that, it only needs to have one derivative, and it only has to have one derivative in L2. So it doesn't even have to have sort of second derivatives sort of somewhere, right? This is all you need. Okay. So if U satisfies this thing, I'll call it W for weak. For all B, we say weak solution of you can start to see why these are called test functions, right? This is something where you have to like check something is true at every point. But if you multiply by a test function and do this, it's just, does this number equal this number? Right, so it's like, I'm just seeing if this U is possibly a solution. I'll test it, multiply by some function, do this, and then this has to be true. Doesn't make it a solution, right? But at least, you know, it's passing a test that it is possibly a solution. And if it's true for every test you give it, then it's, you know, a valid solution. Now, if F is actually continuous, then U that comes out of this is continuous with 2 second derivatives, and you can undo the integration by parts, and you get that this thing is true, you know, in an integral sense for every phi, and the only way that can be true is if you have a strong solution. Right, and then this is called a strong solution. Now, if F is discontinuous, you still get a unique solution out of this problem. And it's the same weak solution that we've seen from the other techniques, which is, in my head, I think that's hard, but maybe if you look at it the right way, it's trivial. I'm not sure. Okay, but it's true. Okay, before we get on to the finite element method, I had a couple of things to put in here. Okay, so there's some theory which says that the weak solution that comes out has L2 second derivatives bounded by the function in the L2. Right. This is exactly the same kind of thing we got from the Green's function for if F is continuous, then u has two continuous derivatives, and the size of the continuous derivatives are smaller than a constant times the size of f. Okay, and so this is just an extension of that, and you can get it from the Green's function formulation as well, or the Fourier series representation in the periodic case. I guess there's just one other thing I want to show you before we go on, which is another way you can get this problem. So another formulation. E1. I can look at the following functional. A functional is something that takes a function and gives back a number. Okay? So what comes out? I'm going to give you this function, which is in HP1. E is suggestive. It's for a kind of energy. This is a mathematical energy, not a physical one, though. And I look at this. 1/2 u prime squared plus 1/2 u squared minus u times f dx. That's sort of quadratic. It's bounded below. Okay, that's something you have to do a little bit of work to find out. And if you have a quadratic function that's bounded below, it has a unique minimum. So we will show that if you minimize this and u is the minimizing function, so the way you write that, it's the argmin. So there's a minimum value of E, and this U is the U that gives you the minimum value of E. That's what that says. So we will show that this satisfies W. Okay? The way you do it is you make a test function, right? And you go, if U really is the minimum, then if I move away from the minimum, I have to make the energy bigger. Right, so that if I take this thing, this will be strictly positive. Well, okay, this is for epsilon not 0, and phi not identically 0. Okay. So let's look at that. That says the integral from 0 to 1/2 u prime plus epsilon phi prime squared minus u prime squared plus u plus epsilon phi squared minus u squared minus u plus epsilon phi times f plus u times f. This all has to be positive. Okay, and you'll notice that there's a bunch of terms that cancel out. U prime squared minus u prime squared, u squared minus u squared, u times f, u times f. Right, so let's look at what's left. There's some epsilon stuff. And what does it look like? U prime, phi prime, because there's two of them and a half. And then there's a UF, same thing. Oh, UB minus phi f and be a little bit careful, right? The epsilon squared stuff is just epsilon squared size times the size of phi, right? So that's just some number times epsilon squared, everything that's left over, right? And this has to be positive for every epsilon that's not 0. Right, so I can make epsilons, like, if this is not 0, right? Okay. Oh, yeah, okay. Yeah, I'm going, oh, now I'm in trouble now. But no, no. Like, if this is not 0, right? Then it's got a sign. And however big it is, I can make epsilon squared small enough so that this term doesn't count. Right? And if this is positive, like epsilon is not positive, right? It's any sign I want, right? And so, oh yeah, if this is positive, I can just take this to be negative, and then this is not true. Right? And if this thing here is, okay, help me out, what did I say first? If this is negative, right, then I take epsilon positive, and then this isn't true. Right? So the only way this thing can actually be a minimum is if that quantity has to be 0. I guess I should put greater than 8. This has to be 0. Okay. Oh, well, I think the argument still works if I do that. Right, and then that's exactly this thing here. Right, so I can get the weak formulation from this energy minimization. Is anyone taking Math 402? Right, calculus variations? So this is something where you're trying to minimize. This thing comes out, right? And now you're thinking that, you know, f is actually like continuous and nice. And so then you can integrate by parts, right? And then you know that this has to be true. And then this thing here is called the Euler-Lagrange equation for this energy minimization. Okay, that's Math 402. Okay, so for us, it's just an extra way to look at this problem that comes up, which we're going to do numerically. Okay.
Oh,
Sure. Oh, a bunch of
sorry.
questions.
No, I'm just confused. I might have missed the beginning. What is the, I suppose, problem that this solves? So like you'd say the problem is this, and the weak solution shows that this is.
Oh, so let's suppose that you find a U that satisfies this for every phi.
Okay.
Right? It's solving this problem.
I see. Okay. Oh, okay.
Yeah.
Okay.
Yeah.
Thank you.
Yeah. And it's solving it, you know, generalized to the way that's been done before, where, you know, if f isn't continuous, like if it's got some singularities or discontinuities, you can still make sense of it from the Green's function, from the Fourier series, and now, of course, it makes sense here because you only need one derivative, you don't need two.
Right.
Right. So, okay, does that help?
Yes.
And then you had a question as well? No? Oh, you did.
I think there might be the factor of 1/2 I add to the f terms on the right side as well. Just comparing like the EU, this end of the board to the EUs on the right.
Yes, thank you. Okay, but then I need a dx, so I don't know what I'm dx. I hope it's right in the notes. I've already admitted my weakness for plus minus. Okay, half. Okay, yeah, just a number. Yeah, you go out with friends back in the days before, you know, individual checks and the percentage tip button. And they say, well, you're a mathematician, you can work, okay, come on, it's a number. That's so uninteresting. Okay, there you go. Where are we going? So, you've already seen that there's a sort of a difference in the philosophy of approximation that we can take. Finite difference method. What was it? You're approximating values on a grid, right? And with the spectral approximation, you're actually approximating a function. You've got an approximating function, u of x. Now, okay, in the end, to make it efficient, you only evaluate the function on a grid, and we're going to get some of that same kind of flavor coming up. I'm going to talk about subspace approximation. Subspace approximation. Okay, I really like this way of presenting the finite element method, but of course you could tell me at the end whether you like it too. So I've got this space HB1, right, where my function u, that's the weak solution, is in. But you can't compute functions in that space, right, because it's like infinite number of values. So what you do is you say, well, I'm going to have a finite dimensional subspace, like the n terms in a Fourier series, right? So let's do that, but we're going to be more general in our subspaces. So we're going to have an n-dimensional subspace. S for subspace of H. And we're going to have a basis for it. So there'll be n functions. Right, and then the space is just a set of all linear combinations of those basis functions. In many of the basis functions that we pick, in fact, ui will be values of the resulting function at certain points, but that doesn't have to be true, right? Okay. We could have functions that correspond to sort of derivative values or integral values of u. So this is sort of general. But I can make it concrete where the ui's are in fact the values of the solution at some points. If I set the basic idea where I'm going to take the set of piecewise linear functions on orbit. This is a familiar idea from our linear interpolation way back at the beginning of the course. So I don't need the grid to be equally spaced. Right? I'm thinking of this periodic problem again, so I'm going to have a grid point at the end, but I don't have to have one at the beginning. So I'll have, x1, x2, x4, x5, and then x6. So n will be 6 in this case. Right, and what are the kind of functions I can get? Well, if they're periodic, then the value at the beginning and the end has to be the same. But it's just going to be piecewise linear, but continuous. Okay, there's an example. Right, continuous. This function is Doesn't have a continuous first derivative, but it does have derivatives that are nice enough that it's in this space, right? So these functions are, this is really a subspace of HP1. And the basis vectors are just the linear interpolants where I've got value 1 at one grid point and value 0 at all the other grid points. So the phi looks like x I minus 1, x I plus 1. It's going to have value 1 here and be a little hat. And 0 everywhere else. So if I take the values u on the grid and I multiply by those functions and I add them up, I'll get exactly this thing. Right, so here the coefficients are actually the values of u on this grid. So just like with the spectral method, like we're starting with this functional approximation, but you know, it's also kind of nice to make things concrete and think about, you know, there's some values on the grid you're computing as well. Right? Okay, but it's a mix of both. Okay, so of course I want to find unknown functions, but for now let's just do some interpolation, right? So I'm going to consider a known function. And I'm going to find functions that are close to it that are in this space. Well, if you had two derivatives, right, I just do piecewise interpolation, right? I just take u to be the values on the grid. Do piecewise interpolation, we'd be back in week 1 of the course, right? We'd have a second order, like functional approximation. I want to do a little bit better, right? That's a candidate of an interpolation. I want to find the best one, right? So I want to find u of x in the subspace that is closest to the exact in the HP1. So I want to minimize the coefficients of the values of u on the grid, because that gives me this capital U of x, right? Because it's just those values of u, right, times this. Of the thing in Sn minus the exact solution in HP1 squared. Right, it's easier to minimize the square than it is to minimize the absolute value, right? Because one has continuous partial derivatives and the other one doesn't. Right, so this is 2 minutes. The HP1 has the value squared and the derivatives squared. Right, and if I put in what this u is, this is the sum of I equals 1 to capital N ui phi I of x minus u of x. And this is the sum of prime squared dx. Right? So this is a scalar function of a vector. The phi's are known, the u is known, the thing that you're trying to pick so that this is the minimum are these numbers, these n numbers. Right, so this is a function from Rn to the real numbers that you want to minimize. Right, and how you do that, which we'll do next time, is you just take the partial derivatives with respect to ui, and you set them all to 0. Right, this is a quadratic function. It's got a minimum. How do you know where the minimum is? It's where all the partial derivatives are 0. Right, because if they were positive or negative, you could change that variable to make the thing bigger or smaller. Okay? So we'll, oh, there's no good time to break, but this is as good a time as any. Next time we'll take the partial derivatives and see what comes out. And remember, I can do interpolation with the actual function values. I know what u is, right? And we know that's accurate. And what comes out of here is even more accurate in that norm, right? Because it's going to be the best you can do. Right? Then we're going to go back and say, well, the best I can do is got to be better than if I just do interpolation. So then you'll get an estimate on this best thing, how accurate it's going to be. And then we'll get to the finite element in a tricky way. Okay, next time.